Welcome back to mathkernel. We have scalar products, lengths, angles, and we've met orthonormal bases in passing. Today we make the language precise, prove the one trick that turns any orthogonal set into a unit 1, and then read a vector's coordinates straight off with nothing but a scalar product. Let's start with the vocabulary, because the precision matters here. An orthogonal system, an OGS, is a set of vectors, none of them zero, that meet pairwise at right angles. Their lengths are left completely free.
So on the board, V1 and V2 are perpendicular, but one's long and one's short. Right angles, nothing said about size.
Exactly. Now add one demand. Every vector has length exactly 1, and you get an orthonormal system, an ONS. That condition is compact enough to write with a single symbol, the Kronecker delta. The product of any two is 1 when they're the same vector, 0 otherwise.
Convenient notation. But an orthonormal system, is that automatically a basis? Do I get to build the whole space out of it?
Not automatically, and that distinction is the third word. An ONS becomes an orthonormal basis, an ONB, only once it's also a basis of the space, enough vectors to span everything. Every ONB is an ONS. The reverse can fail.
So it's a ladder, right angles, then unit length, then spanning.
A ladder with the arrows pointing one way. And the reason an orthonormal basis is worth all this fuss is what it does to coordinates, which is where we're headed. 3 words, 3 precise claims. OGS is right angles. ONS adds length 1. ONB adds spanning the whole space. Keep them straight, and half the marks are yours. So suppose you already have an orthogonal system, but the lengths are all over the place. Turning it into an orthonormal one costs nothing but a scale factor per vector, no rebuilding required.
On the board, the dashed arrows are the original ones, long and short. You just shrink or stretch each to length 1.
Exactly. Divide each vector by its own norm. Scaling changes length, never direction, so the right angles you already had survive untouched. The product of two rescaled vectors picks up a 1 over the 2 lengths factor, and since the original product was 0, it stays 0.
Fine, the angles survive. But does dividing like that quietly shrink what these vectors can build, the span?
It doesn't, and that's worth its own name, span invariance. Each new vector is a non-zero multiple of an old one, and each old one a multiple of a new one, so anything you could reach before you can still reach. Same subspace, cleaner ruler.
So the practical order is, get the right angles first, worry about length 1 only at the very end.
That's the right instinct, and it's exactly why the process for building these, next video, saves the normalizing for its final line. So orthogonal is the structure you work for. Unit length is a free rescale on top. Never do the second one first. Now the payoff. In an ordinary basis, finding a vector's coordinates means solving a linear system. In an orthonormal one, each coordinate is just a single scalar product, no system at all.
So I take x, and its coordinate along each axis is what I get by dropping it straight onto that axis, the dashed lines on the board.
That's the picture. Here's why it's true. Since the basis spans, x is some combination of the b's with unknown coefficients lambda. To find lambda k, take the scalar product of both sides with bk.
And that's supposed to hand me the coefficient directly? No system to solve?
Watch it collapse. Bilinearity spreads the product across the sum, and the orthonormal property, the Kronecker delta, kills every term except the one where j equals k. What's left is lambda k alone. So the coordinate is exactly x dotted with that basis vector.
So the whole vector rebuilds as the sum of its shadows on the axis.
That's the Fourier formula. X is the sum over each axis of its scalar product with that axis, times the axis. Every coordinate, one dot product, done. So an orthonormal basis turns geometry into arithmetic. Coordinates aren't solved for. They're read off, one scalar product each. The Fourier formula gives coordinates. Feed it into the length, and you get something just as clean. Take the norm squared of x and substitute the sum.
Two sums multiplied together, that looks like it'll explode into a mess of cross terms.
It would, except orthonormality steps in again. Every cross term carries a product of two different basis vectors, which is 0, so the whole mess collapses to the diagonal. The length squared is just the sum of the squared coordinates. That's Parseval, Pythagoras, working directly on the coordinates.
So the components are the legs of a right triangle and x is the hypotenuse, the marker on the board.
Precisely. And now the sharp version. Everything so far assumed a full basis. What if you only have an orthonormal system that stops short, not enough to span?
Then the sum of squared coordinates can't still equal the length. Surely you're missing directions.
You're missing directions, so you can only fall short. The sum of the squared coordinates is at most the norm squared. That's Bessel's inequality. Inequality holds exactly when x already lies in the span of what you've got, which is precisely when nothing is missing, back to Parseval. So Parseval is the full story. Bessel is the honest partial one. With a complete basis, coordinates account for the whole length. With less, they can only undercount. Let's ground all of it in one concrete case. Two unit vectors at 45 degrees to the axis, and the vector x equals 3, 1. First, never skip the check. Confirm it really is an orthonormal basis. Both have length 1, and their scalar product is 1/2 of 1 minus 1, which is 0. Two orthonormal vectors in the plane, so automatically a basis.
So now the coordinates are just two dot products, no equations.
Right. X dotted with U1 is 1 over root 2 times 3 plus 1, 2 root 2. X dotted with U2 is 1 over root 2 times 3 minus 1, root 2. Those two numbers are the coordinates, full stop.
Prove it lands back on x. Plug the coordinates in and show it reconstructs.
2 root 2 of U1 plus root 2 of U2 gives 2, 2 plus 1 minus 1, which is 3, 1, exactly x. No linear system anywhere in that. And Parseval seals it. 8 plus 2 is 10, and 3 squared plus 1 squared is also 10. Coordinates, reconstruction, and length all agree. Let's gather it up. OGS, ONS, ONB are three promises stacked in order, right angles, then unit length, then spanning, and only a risk scale takes you up the first step.
And once you're at a genuine orthonormal basis, coordinates and lengths are just scalar products, the Fourier formula and Parseval. Fine, but that's all assuming someone handed you an orthonormal set to begin with. What if they didn't?
That's the chapter's opening move. Today we assumed the right angle vectors were handed to you. Next time we stop assuming that and build them from any basis at all, the Gram-Schmidt process. So, orthonormal bases make the arithmetic effortless. Next, we earn one from scratch. That's orthonormal bases and the Fourier formula, the precise language, and coordinates you read off with a single scalar product. Thanks for watching. That's everything ready in this chapter so far. More on the way.